So this is video 8.5, the last one about energy and work for Physics C. We just have a couple more topics, they're closely related, and that's what if you have a system and there's an external force, or say internal non-conservative forces acting and doing work in the system. What happens to energy there? We clearly can't still use conservation of energy, because if we have an external force doing work on the system, the energy of the system is going to change. But the good news is, if we know something about the force, we can figure out how much work it does and modify conservation of energy there. Essentially, the change in the energy of the system is equal to the work done by the external force. So if I'm doing positive work on the system with an external force, what I'm doing is I'm putting energy into the system, and if I'm doing negative work, I'm taking energy out of the system. So, quick example. Let's say you throw a 5 kilogram bowling ball 1.4 meters into the air. Don't ask me why you're doing this. You're crazy. Anyway, the question is, how much work did you do on the ball-Earth system? Notice that I had to put the Earth in the system, or at least the Earth's gravitational field, so that gravity can be an internal force when we talk about potential energy. So what you do is what you're doing, really, is you're changing the energy of the system. And the energy of the system, or the change in the energy of the system, is the change in the kinetic energy plus the change in the potential energy. Now the change in kinetic energy is zero, because before you throw the ball it's at rest, and when the ball is at the top of its trajectory, its velocity is zero. So delta K is 0. Now delta U, on the other hand, is just mg delta H. And that makes this really easy. We can figure out how much work you did by plugging in numbers. So 5 kilograms times 9.8 meters per second squared times delta H is 1.4 meters. And this works out to be 68.6 joules. That's how much work you did. So problems like this, they can get complicated, but the concept itself is pretty easy. If you can do conservation of energy problems, you shouldn't have any trouble with these. A related topic is friction within a system. So you've got whatever your system is, and you've got two parts of your system. Those have friction between them. Well, we know that friction is not a conservative force. And so that means that if there's friction in your system, you usually can't use conservation of energy. But the question is, what does friction do? It's a force, so it's going to change the energy of the system, generally decreasing it. The question is, where does that energy go? Well, it turns into what we call dissipated energy. Sometimes heat, I'm actually going to change that dissipated as a better word. Essentially, it makes the individual molecules start moving and jiggling around, and so that's where the energy goes. In practice, it means the temperature increases a little bit. That's why if you, say, touch the brakes on a bicycle or a car right after you've stopped from high speed, they're going to be very hot because all that kinetic energy was converted into dissipated energy and increased the temperature of the brake rotors. So this example, we've got a 1,200 kilogram roller coaster, starts from rest, height 20 meters. At the end of the ride, the roller coaster has a speed of 11 meters per second and a height of 3 meters. So the question is, how much work did friction do on the coaster? Well, our system here is the coaster, the track, and the gravitational field. And so here's a picture of the roller coaster. There's the ground. Starts off at 20 meters. Ends up at 11 meters. No, wait, 3 meters. I'm not reading my own problems. And at the end, it's moving at 11 meters per second. Well, the work done by friction is just the change in the mechanical energy. So we can treat it almost as if friction is an external force, except that it's taking energy away and turning it into dissipated energy. So the work done by friction is equal to the change in energy of the system. So that's change in potential energy plus change in kinetic energy. Change in potential energy is mg delta y. The initial kinetic energy is equal to 0. So the change in kinetic energy is 1/2 mv squared. If we plug numbers into this, delta y is equal to 17 meters. So that's squared divided by 2 minus 9.8 times 17. And we find that the work done by friction is, first off, it's negative, which we expect, but it's 127 kilojoules, which is a lot. It turns out that most of the energy that it had at the beginning was turned not into kinetic energy, but into dissipated energy. If you remember from chemistry and last year, all the stuff about heat capacity, you could get an approximate value for the amount the temperature of the track increased, but we're not going to do that because that's not part of Physics C and it would make this problem a lot more difficult. For tomorrow, I'm going to check questions 8 and 9, but you should be able to do the rest of the chapter 8 problem set.